how do we use those projections to create a picture of the two-dimensional object. And our two-dimensional object is a map of the linear attenuation coefficients as a function of position in the xy plane. What we're going to look at is a very simple way of creating a picture using those projections. And this simple way is called back projection. And so if I have a set of projections through my object this way, and this is a very simple object, it's only got 9 pixels, and most of them are 0, except for in the center I have a peak, right? And so I'm going to try and reconstruct that object. When I take my projections, when I go through here, I get 0 attenuation. When I go through here, I get 3 because it's been attenuated by this part of the sample, and here it's 0. A projection through here is 0, 3, and 0, and again, projections diagonally are 0, 3, and 0 out here. So what I can do with these projections is just assume initially that if I have a 0, a 3, and a 0 here, I don't really know, given the projection data, whether or not, what the distribution of values is across this row, but all I know is its sum comes to 3. And that's the only thing I know at this point. And so what we can do is we can just back project these values back into the rows or the directions from which they came, and just assume that these values are equally spread across that direction. And this is naive back projection. And so my first iteration of this from my back projection of this data would be these would all be zeros. I'd split this 3 across this row, and so each one's 1. That way its sum comes to 3, and these are 0, right? And in the same way, I would back project my data diagonally, and so I would add a 1 to each diagonal element, and I'd add zeros to these diagonal elements, given the fact that my diagonal data was 0, 3, 0, right? And so when I add 1 across this diagonal, I get a new value of 1 here, new value of 1 here, so these were zeros, and then this one moves to 2. Right? So that's from 2 projections, I now have this picture. From the third projection, I would add zeros in this direction. Right? I'd add 1s all along this column since my sum is 3, so I add 1s along here, and then I add zeros here. And so now I'm to this picture, right, where the middle is 3, and I've got 1s around here. And then if I back project this way at minus 45 degrees, in the same way, I put zeros across here, but 1 spread out throughout the diagonal, and this is my final picture. So that's an image of a 9 or 3 by 3 object using 4 projections, right? And it's not a bad picture when you think about it, right? It's pretty darn good, right? If you took the baseline off, you'd get the actual answer. So this is naive back projection, and that's what was done in the early days of clinical CT, and it's still done to this day. After we'll see there's some modifications you do to it, because it can be done very quickly, right? You don't have to invert a huge matrix of equations. You just back project this data and paint a picture, essentially. If we look at what a picture will look like that's larger, that has more pixels, obviously we need more projections, right? Because if I only have 4 projections, I'm going to get like a streaky picture with 4 streaks through it. So here's let's say this object is a disk at a specific location in the xy plane. And when I take my X-ray view here, I get attenuation as a function, which is the projection of a disk. here. And then at a different angle, I get my attenuation looks like this. Relative attenuation looks like this. Remember, this is this g function, which is the negative log of the intensity over the transmitted intensity. And so that's that one. And then this one, it's here. And so I can tell you, okay, it's somewhere along this column. It's somewhere along this row. And it's somewhere along this, diagonal here. And when you back project those three views, you get this picture. Again, it's not terrible. It's sort of telling you, regionally where this thing is. But it's also, this picture would indicate that there's signal out here, in these lines. And that's just artifact. That's not true, right? If we go to a large number of views, let's say 128 different angles, and back project those, you get a picture that looks like this. And now it starts to look fairly reasonable, right? The one issue with this picture, and we'll see why, is that, if this is a disk, it should have sharp edges, and it should just be a circle in the plane, right? That's the true image. That's the underlying true object. The object that we construct with this naive back projection, this simple back projection, actually is something that is quite fuzzy or hazy. And so when you move away from the center of that object, actually the signal decays away with 1 over r, it turns out, as opposed to just going straight down where the edges of that disk are. And so we lose spatial resolution in doing this procedure, right? The image gets blurred in doing this simple back projection procedure, even though it's super cheap computationally. I mean, you can do it very, very quickly, even with a very large, 256 by 256 or 512 by 512 image. So in order to understand how we should do the back projection, we're going to look at some of the math of how you set up what the projections represent in terms of the object, the underlying object. And so we're going to review a little bit here. Recall that the equation of a line through the plane, through the xy plane, can be parameterized with an angle and a distance from the origin, right? And so this was that distance from the origin, and this theta is the angle. And so that gives you this line through the plane. And the data that is projected, or the attenuation that happens as the X-rays pass along this line, we're going to measure with our detector on our CT scanner. And so L, this variable here in the parameterization of the line in the plane, is essentially equivalent to detector number, or position of detector along our detector array. Okay. And then theta is just the angle at which we have arranged our measurement with the source up here and the detector down here. Recall mathematically, we're assuming that our source is actually rastering across here and we're getting parallel beams. That's the underlying math assumes that. And we saw last time, when we have a fan beam, we have to take into account the fact you're getting multiple beams, but they're at different angles simultaneously. The math, we just group all of the angles together. Right? Okay, so this function, right, we're going to then parameterize g. For any given theta, I have a one-dimensional function in L, and it's this little g. And recall that little g we defined as the natural logarithm of the intensity of the measured X-rays divided by the intensity of the transmitted beam. So that's sort of the fractional amount of X-rays missing is this thing. And so this number will be between 0 and 1. We take the logarithm of that, right? And we know because it's 0 and 1 it's going to be negative, so we put a negative there, and then that is equal to mu, right? The integration of mu across there. Once you do that log, we get rid of the exponential. So that's what g is, right? And when we plot it, we get some positive function, right? That's here, and we're going to get a unique one for every theta. So now we have a two-dimensional function, GL theta, right? And mathematically, when you ask, well, what is GL theta with respect to your original object, fxy? And remember, in our problem here, I don't know why Princeton links do it this way, but fxy is mu xy. It's the linear attenuation coefficient as a function of position, but this is our function that we're getting projections through. And we multiply it by this is basically a line delta function, right? The line response function, where we multiply fxy and we get all of the values along that line, right? When we multiply it by this. And so for a specific setting of L and theta here, G is just the integral over this term, and it integrates that function along this line. Okay? So it's just basically to get the algebra so that you can express GL theta appropriately. Okay, that's the simple integral formula. So now we've related GL theta to our original object and the geometry of how we're sampling it. That's what this equation does, right? Okay, this thing is very famous, and it's called the radon transform of fxy. Right? And this goes back to Johann Radon, back in the early part of the 20th century. And he proposed that if you had enough of these, if all you could measure is these things, these projections, if you had enough of these, you could actually solve for this. Mathematically, that was unknown at the beginning of the 20th century. Like, if I had an infinite number of these things, could I uniquely solve for this? Right? And it's not intuitively obvious when you look at it just out of the box that say, if I have integrals all the way through the object, so I'm blurring all of the details of the object down that line, and all I get is the integrals. But I'm going to get those integrals at different angles. Is that enough information to invert it and get the object? It's not patently obvious that that's true, right? And does anyone think, oh no, it's super obvious because everyone got an idea? I don't. When you look at it, you think, oh, you're going to blur all of those signals together. Am I sure that I can put this thing back? Analytically, you can do it, right? Okay, and it's called the radon transform. Very famous. So this is a review slide. We have our measurement here on the detector, and we're going to take the radon transform of the object, which is what we measure. We're going to take those measurements and figure out what mu xy is. Okay, where mu xy is this. Review again. This is, remember this, what is this arrow? Yeah. This is a 3D object looked at from different directions. The CT problem we're solving is for any slice of this object. If I cut it this way, then I have a 2D function, which is brightness in the plane, the perpendicular plane cutting this object. This shows a simultaneous set of projections. And so I have 256 of them, simultaneous slices. And then these are the raw data. So if I took a cut through the object here, this is basically 3D data as I'm turning around. That would give me enough data to reconstruct that slice. Okay, as I have all of these angles as I'm turning around. Okay. This, remember, is not the G function. This is actually the actual measured image intensity on my detector. And then you take the log transform, you divide by the basically illumination intensity, take the log and you get rid of this exponential, you wind up with this. And that's what it looks like when you take the log. Not that object, obviously, but you get bright signals where you have high attenuation. And then when each one of these 2D slices, you can think of, whoops, my bad. Each one of these 2D slices is a solution to mu xy, where this is x and this is y. Right? And we're just doing, in modern CT, you're doing like 256 of those simultaneously. Right? For those of you who are thinking ahead, obviously, if you solve the problem in 3D, right, you can solve the problem in 3D, like a 3D projection, as opposed to just thinking of it as stacked 2Ds. And as the geometry gets more weird, like as that cone in Z gets bigger and bigger, obviously the planes aren't parallel. And so you eventually have to take into account that you have this three-dimensional set of beams as opposed to a set of two-dimensional set of beams. We're just going to think of it as a set of 2D. So there's that graphic again showing G of L theta. This is L. I got 3 different thetas here, right? And I back project those. So this is a fun movie where this is the back projection of one single GL theta through a human head. Okay, so we take one view and I back project that single view and it looks like this. Right? You can't really tell that's a human head, right? Because obviously all of the values are just like spread out over where they were obtained. However, if we play the movie and we just add views, so each one of those pictures was just adding the next view in, right, to that solution. So here I'm rotating through, I'm just adding more and more views as I go through. You can see the rotation of the detector and the gantry and what angles are being added in, right? And I'm back projecting a new one, back projecting an additional one, back projecting an additional one. And basically you sort of in a sequence, you just sort of paint edges as you back project from different angles. You can see at this point, I have pretty good estimates of the edges of things in this orientation. And that means I've already back projected where my source was here and my detector was down here. And so those edges are well sampled, right? However, the edges up here, I just haven't got any data to make a statement about those. And so the back projection just smears those data all together. And then as the gantry rotates around and picks up information on those edges, it paints them in. Right? And then you get finer and finer details as you get higher and higher angles. Until finally you have this, and this is probably a 512 by 512 or 256 squared image, and you get really nice details about all of these small structures in here, right? And a lot of edge information. Any question about that? It's pretty intuitive, right? You're just like pushing those back. Now, those projections actually weren't. Oh yes, yeah, question.
If you make a reconstruction like this with say 256, is it really necessary to keep going at higher resolutions or higher, like sort of where do you hit that wall of you're taking more pictures than are useful for being able to interpret any more detail?
Right. I think that's a really good question. Is sort of why or where? What's the cutoff of resolution? I mean, eventually, do you run out of interesting things to look at higher and higher resolution? And it depends what you want to see. If what you want to see in a patient is the true Hounsfield unit number for a large tumor in their liver, say they have a tumor that's 1 centimeter across or 2 centimeters across, and what's important is when you inject a contrast agent, you need to know the exact value of how much contrast went into that tumor. And so all you need to know is the number. You don't have to find it. You know where it is, right? So under those conditions, you don't really need high resolution. You know where the thing is. You know it's a blob. You just need to put your region of interest on it and measure the actual value. So that's when you don't need high resolution. On the other hand, if you're looking for something that's really small, for example, say a really small piece of calcium in the wall of an artery. And when I say really small, these things come in very small sizes, like they're 50 microns across. The early ones that you all, as 20-year-olds, or whatever you are, have little pieces of calcium growing in your coronaries that you can't see right now when you image them because they're too tiny. But half of you are growing them at a fairly good clip, and half of you are growing them at a slower rate, right? Those of you who are growing them at a really good clip, you might want to know, right? Because when you're in your, say, late 30s, you should start taking a statin, right? Because it's just good for you, right? I don't know if I could get in a lot of trouble saying that, but it just is. Just look at the data, look at the Jupiter trial or anything, right? So those things are really tiny. And so basically, the farther you can go in terms of high resolution to find those earlier, the better, right? So there is no end to that resolution need because they just go down to tiny little objects. That's a really good question, though. I was like, what's good enough? It becomes a really practical question when you ask, how many x-rays should I use to image this person? Because the more x-rays you use, the higher resolution you can achieve. And you don't want to irradiate them such that they get 10 years worth of background radiation or 50 years worth of background radiation. You'd like to, keep them sort of in a couple of years or something. So, all right. So we can organize that function GL theta, right? So L, remember, is the direction along the detector. Theta is just the angle of views. And we can organize that as a two-dimensional, brightness function in the plane. And normally the way it's displayed, for whatever reason, is L along one axis like this, and then we just stack the different views along this direction. So this is theta, and this is L. Okay? And if this is our object, right, we're assuming this GL theta is the data from parallel beams going through this object. So you can make that assumption right now, even though for most scanners we get these fan beams, but when it's organized like this, we're going to put that all together, right? So that we'll compensate for that. So if I'm projecting through this object, right, when you look at this thing called a sinogram, you can see certain features in this object over here, right? They're pretty obvious what you can see, right? And the first obvious object or thing you can see over here is this big edge, right? So this edge here is simply the outline of the whole object, right? So when it's at its maximum dimension, you know that projection is this way or 180 degrees because this is the maximum dimension, right? As we change our angle of view and it goes narrower, then this thing is what we're projecting across here. Right? And then these two dark circles, you can see those features riding through the data as we take different views, right? So if you're really good at CT, you could look at this and know what it is, right? If you're really good. So let's take a look at a specific GL theta. So let's ask a question. What projection is that? Can we figure that out? We know that, okay, this over here, we get a very low number, right? So mu is very low. So it's probably what material? Air, right? So this would be the air because mu is super low. Okay, these look like air pockets in the phantom, right? So here, that's probably one of those air pockets, right? And that's probably one of those air pockets. Is there any other thing that can tell me which view this is? Yeah? This guy, right. Yeah, this is not symmetric, right? There's some junk over here, right? And all this stuff down here. Okay. So therefore, you know that we're projecting through this way. This L, if I draw this down here, is over here. Okay, so we know that orientation. And then we also know that we go through 180 degrees and see it back on this side, right? So we rotate all the way around and see it back on that side. That's a good observation. So I don't know why there's all these letters on here. Oh, I was going to do a poll. This is from before. We're not going to do this today, though. We're going to run out of time. So theta in this direction, L in this direction. Theta 0, that's it. We can ask the question, well, which direction is theta 0, right? We know that theta 0 is when we have a maximum diameter of the object, right? So theta 0 is either looking down this way, our source is here and our detector is here, or our source is here and our detector is up here, right? We know that when we get to 90 degrees, this is on the left, right? So that's this one. Right? No, wait a minute. That would be this one, right? If L is bigger this way, all this junk is in a small coordinate, and so L is plotted this way. This stuff is down here, so that's D. So then this would be 0, this would be D, right, as we roll down this way. When we start playing with these things in MATLAB, you have to remember that in MATLAB, things start here and they move down as rows and move out as X, right? As opposed to an XY coordinate system where you have a 0, 0 here and they move up this way and this way. I'll just remember that. Okay. Here's another point. Feature when you're looking at a sinogram. So we're going through different angles. And then when these two features cross, that means that they're overlapping each other, right? And when the two features are, oh, this is showing this junk here is here. And so that's a pretty simple object, and we can see all these features. When you have a whole pile of objects, the sinogram itself starts to look a little complicated, right? So it would be very difficult to look at this sinogram and say, oh, I know exactly what that is. Again, this is the example out of your book where L is along this direction, theta is this way. I think I painted these coordinates in, so I might have figured out at one time or another, what views are what here. So it looks like 0 looks probably vertical because see all of these gaps here? That's when we hit one of these zones, right? Where we have an air signal sort of going through here. Anyway, by Radon's hypothesis, if you have this function, this continuous function, that's enough information to tell you what that function is. Right? So now we have going back to our sampling, we need to know, well, how finely do I have to sample this in order to reconstruct this to within the tolerance that I want? Right? And so now it's just a sampling problem. So back projection, let's look at it mathematically. If we have, this is one back projection image for a single angle theta, and it equals G along the line, right, of that line, theta at that angle. So it's a two-dimensional function in the plane, but it's basically a set of parallel lines, right, where the g value is projected to every single pixel along that line, right? So that's one of the projection things. So that's a single, back projection. And then the summation, this is sometimes called a laminogram, which is the summation of all of these things. Basically, you just add them up together. It's very simple, right? So I get back projections. It's a function of x, y. It's a set of parallel lines of different brightness. And I add them up over theta here, just integrate them here, and I get this picture. And so it's a reasonable approximation to the object, but you can see there's this haze in the background, and that's from all of these projections projecting data into places it shouldn't be, right? Now it's intersecting more often at places that it was sampled from, but it's still, projecting a lot of data out into space where there is nothing there, because you look at one of these bees, and it's projecting information out to here. There's nothing out there, but it's putting signal out there. So there's this little MATLAB script that I've put on the website, and you guys can fool around with it to look at what happens when you sample the radon transform at different rates, and what happens when you, say, drop out just whole chunks of data, right? So we can pause here for a second and run this program. Okay. Let's go back to here. All right. So it's a really simple script, and you just run the whole script every time. It just clears all of the results from the last time you ran it. You can use a central square image of small squares that have 1 pixel separation between the squares, so that you can see whether or not you can resolve that separation of those squares. So it's like a resolution test. MATLAB provides the Shep-Logan phantom, which is this phantom. So you can use that. You just set whichever one you want. You set to 1. You set the rest to 0. And then I have a human coronary CTA, which I will put on the class website, which is a TIFF file that you can look at a real picture. I have to take out a few things from the picture first, though. Okay, so we can, for the Shep-Logan phantom, we'll set that. It's simple stuff that you probably figured out how to do in MATLAB from the problem set. And then if we just construct the small square image here, that's all simple stuff. We're just constructing a picture. And then there's the coronary picture. So then we look at the Fourier components of that 2D function I, whatever one we're looking at. We decide on how we're going to back project our picture. And we have a first projection, a last projection, and a delta theta, which is what is the angle between projections, subsequent projections. So if it's 1 degrees and my first projection angle is 0, my last is 180, then I would have 181 projections that are going to go back into creating the picture. If it's 18, then only 10 projections are used to create the picture. So you can play with this parameter to figure out how does my image quality change as I change the number of projections. And it uses the intrinsic radon transform that is given with MATLAB. Okay, there is a radon function. And so the radon transform of the image is just radon I, and then we resample this to test what happens when you subsample this, right? If you sample it adequately. And then So we resample it, and then we take iRadon, which is just the inverse radon transform, to give you an image back. Okay, so this is if you want to look at artifacts from missing samples. Now, you guys are welcome to take this code and then just play with it and discover all sorts of things. Okay, so you just run the whole script each time. So just hit that go, and I think it should come up. Yeah. Okay. We'll look at the window. A nice habit to get into when you're doing this kind of thing is just to label all your figures, and because then it tells you what each one is. So the original image for iRadon looks like this. Okay. And then the first thing we do is look at its Fourier transform. These are the Fourier coefficients for that image. Right? And notice that when you look at the Fourier coefficients, oftentimes what you do is you take the absolute value of the Fourier coefficients, as opposed to, it's a complex number, actually, each coefficient. And so we're not going to look at the phase of it. We'll just look at the amount. Right? So you take the absolute value of the Fourier coefficient. There's a huge dynamic range of their values, and so oftentimes you log that dynamic range. And to do the log, you add 1 just so that you're not trying to take a log of 0 if any of these things are really close to 0. Okay. So that's what the Fourier coefficients of this, the amplitude of those Fourier coefficients looks like. Right? It's a, it's an interesting thing that this set of numbers is equivalent, carries exactly the same information basically, well, if you had the phase, of this set of numbers. They're just absolute duals, right? Makes sense. You've got the same number, right? And in fact, on the Fourier side, you have both the amplitude and phase. These are complex numbers. Parameters of run, you just record like what happened. So in delta theta, we're saying is 18 degrees, and angles are 0 through 180. So that means we got 11 projections, right? And so our GL theta looks like this. This is our sinogram. So this is theta. Theta is increased this way, and this is L, this direction, right? And basically, that you can see there are very few values used here, and we're going to do the inverse radon from just 10 views or 11 views, and this is the picture we get. This guy. So that's just using 10 views, our estimate of that object, right? And they're equally spaced views. You could imagine, well, maybe I should get 10 views but not equally spaced them, like get arbitrary views. You can try that too, right? So you can see the artifacts, these streaks, right, from projecting high attenuation pixels out into space where they don't exist. And so a lot of that happens at these high attenuation pixels on the edge here, right? The next thing that you can set in here is, this is right down the end of the code, if you want to look at what it happens if I take 180 views. So now I have a really decent sampling, but I just block out a whole set of them, right? And we kind of know how that's going to go because we saw that simulation of the head being formed. So if you block out this set, you get this image, and you can see I have very good edge information here and here. So obviously these views out here are giving me this edge information. And then when I come up to the top of the head where I should have another sharp edge here, I just have no idea where that edge is. And so it basically just, it's a blur, right? So kind of a fascinating and somewhat intuitive outcome, right, of what an artifact in CT looks like when you have bad data in specific directions or you undersampled the radon transform. Why would you ever think of doing this, taking only 10 views? Or let's say, instead of 180 views, taking 90. What benefit is there to do that? Say between 180 views and 90 views. Say that again?
Exposure?
Yeah, exactly. So the answer is that you used half the radiation, right? Remember, as we collect data, we're depositing radiation into the patient with this imaging technique. With other imaging techniques, like say if you're doing back projection MR, which you can do sort of, instead of Cartesian MR, you can do polar MR, and it's very similar to this. There, it's just a matter of time. So I can get an image in half the time. And if one image takes 100 milliseconds and one image takes 50, and something's moving, it's better to get it done in 50. And so you get high time resolution, but lower spatial resolution. So you're trading off time resolution and spatial resolution. So these things are always in a balance, right? A CT scanner, the time resolution is an interesting thing because the gantry is spinning at a certain rate, and so you're kind of stuck with how many, with how long it takes to get, say, 180 degrees of views. It's fixed by whatever the rate is. CT scanners often let you change the rotation rate of the gantry. You don't always run it at its highest rotation rate because certain things need greater X-ray fluence, and so you just spend longer at each view getting more X-rays. Okay? So those are all asides. So I would encourage you just to pick up this code, and so that's the missing projections here, and just start fooling around with it. So you can change, here, artifacts from missing samples. The code is like, how do you delete samples in a certain region, and then take the I-rate on of that with the samples deleted. And then sampling is up here where you can set this. So if we just set this to delta theta 1 degree, say, and just run it again, and then bang, 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 but they all come up, and you see here's our new GL theta with 181 views, and that's the image that results. It's not identical to this image. See, there's still a very subtle artifacts here, but it's obviously much better. Okay. So, all right, so let's go back to PowerPoint. Yeah. Okay. Where are we? We're at 11:45. Okay. So we're going to understand by the end of this lecture, I hope, what we have to do to those projections, to the GL theta projection, in order to make the back projection method work correctly. Okay, right now, it's not working that well because we're getting blurry pictures, right, with all that stuff in the background. It's painting data out into space where there is no data. Right? But it turns out we can modify those projections, GL theta, and back project the modified projections such that we get the true object. Right? And in order to do that, we're going to go through understanding the projection-slice theorem, and then we'll take a look at what our projections are in Fourier space, what it means to have these projections in terms of sampling the Fourier space of the function. And then it will become obvious what we have to do to the projections to back project them correctly. So the projection-slice theorem, this is a fundamental sort of theorem that you just have to carry this in your head all the time when you're thinking about CT. And it states that if I have GL theta here, right, and so I'm projecting at this angle, these are parallel beams, and I have GL theta here. If I take the one-dimensional Fourier transform of GL theta, right, remember this is the integration of mu through this on this line and at each point. So now I have a 1D function and I take its Fourier transform, I go into the Fourier space, the 1D Fourier transform of this thing GL theta will be a 1D function. Let's call it capital GK, right, theta. It turns out that that function, when you plot it in the 2D Fourier space, is just a sample along a line through the 2D Fourier transform of the object. This is another thing that, to me, it's not intuitively obvious that this works, right? That when I integrate all the way down through these parallel beams along here and produce this function of this stack, that when I take its Fourier transform, it is simply a line through the continuous Fourier transform of my function. So you should just let that sink in for a while, because you want to really understand what that means, right? Yeah, sure, I can, and I'll say it in a different way. Okay, so let's say I have a two-dimensional continuous function here, right? And it's, bumps and brightnesses and stuff like that. I take its two-dimensional Fourier transform. It's continuous two-dimensional Fourier transform, and let's say it's analytical, and I know exactly what that is. So I take that Fourier transform, and it is this function, right? We know a few of those, right? If this function fxy was just a square here, the two-dimensional Fourier transform would be a sinc, right? A 2D sinc. And so I would know exactly what that function is, right? If this function here was a comb, a set of delta functions over here, when I take the two-dimensional Fourier transform, I just get a set of delta functions over here. Okay, so let's think about that. So now I have some arbitrary function. I take its two-dimensional Fourier transform. I get the exact two-dimensional Fourier transform of this thing, and it's this function. If I take a line sample through that function, I just look along a line and take every value along that line, right? And I take the inverse Fourier transform of that thing, I get GL theta along that line. Or if I take the forward Fourier transform of GL theta, I get a line through the continuous transform. And that's called the projection-slice theorem. Really cool, very, very useful in understanding CT images in terms of their artifacts and quality and their relation to your coverage of the spatial frequencies in Fourier space. Any questions? Say it one more time. No? Okay. Okay, this is, we get into the algebra of this in the book, but I think I have a better way of describing this here. Yeah. So this, we're not going to pause and go through the algebra the way they do it in the book. We might do this later. It's exactly the same way as I'm going to show it to you, but they use a different set of coordinates, etc. So we're going to go here, because this is a more visceral way to describe it. Okay, we have a continuous function, fxy. We have its known Fourier transform, fuv. These are spatial coordinates. We call them k, x, and ky, right? We now have a function, GL theta, and its 1D Fourier transform that's a function of, let's say, rho, position along that line, capital G rho, and they're parametrized at theta, okay? In our coordinates in this course, this is going to be mu xy, this thing in the CT scan, and then this, its Fourier transform, will be capital U kx ky. And then position along this line through this Fourier transform we'll just call position little k at theta. And then this is, as before, GL theta. Okay? So the function along here is simply this capital G of k, which is distance from the origin at an angle theta, is just the Fourier transform of little gl theta, right? As a function of, you take the transform with respect to L, okay? So theta is just a parameter here. We're not doing the Fourier transform. This is all 1D, right? And so this is how it's the projection-slice theorem is set up in our coordinates, okay? In that we get this function gk of theta from gl theta by taking the transform in terms of L. For the next 3 slides, I'm not going to go through them, but you should do these as an exercise, which is calculating this for a function that we know very well, which is this rect function, right? So if little g of xy is a 2D rect function, we know analytically its Fourier transform in kx and ky is this. Remember, this is the product of sinc functions. So this is our rect function. It gets a product of sinc functions. We can look at the particular values, right, of what a projection would be through a rect function, because that's pretty simple. So gl theta at a projection angle of 0 is just the rect function, because we've got that square. When you project down onto the axis, you just get a 1D rect function, and you can prove that its Fourier transform is a sinc. And then you can do it at 90. It's the same thing, right? And then you can do it at 45, and it gets more interesting, right? The fact that the projection-slice theorem will work at 45. You can do it analytically with this simple function, the rect function, right? And so this I would encourage you to go through this example, right? That, remember, little g as a function of L is a function of our position along our detector when we're at an angle of 45 degrees to that 2D rect function is going to be a function that looks something like this, right? In the sense that it'll look right along the central diagonal, we'll have the maximum integral, and it will reduce as we go off to the corners, right? And so you can write down analytically what that is and show that the projection-slice theorem works. There. So now that we understand this, right, we can start thinking about our sampling of our raw data for CT in Fourier space. Because we know if I have an object and this is the function which is its projection along this axis, this should be L, sorry, here, and I know that what happens is when I take the Fourier transform of that, I just get a radial sample through the Fourier transform of our object. Well, one proposal would be, let's just get a bunch of these radial samples at different angles, and now I have sort of a pinwheel of samples through the Fourier transform of the object, right? So if this is, 30 degrees, 60, I don't know what's this has to be 90, right? So 90 over 30, yeah, 30 degrees right here. Then I just take my next angle here and I get this sample through the origin. I take the next angle here, get this sample through the origin. And so this is called a radial sampling, right, of the Fourier transform of the object. So I have uniformly sampled dots along each one of these radii, because when I go back to my spatial domain, the uniform sampling of dots along here are the positions of my individual detector elements in my detector, right? And so they're spaced with some delta x along here. When I take the Fourier transform, I get a uniform sampling along here of the Fourier transform of that function. Okay? So essentially what that tells us is we have far more samples here in the middle as a density than we do out here at the periphery of the Fourier space. So we're sampling the lower frequencies better than we are sampling these frequencies out here, right? And that, kind of makes sense in terms of what we're doing. We're integrating through the object, right? So that kind of makes sense. So one proposal to do reconstruction of CT would be, well, let's just take these data. We know where they are in the Fourier space. Let's interpolate them onto a rectilinear grid in Fourier space, and then do a two-dimensional Fourier transform. And then that should essentially be our image, right? If the fidelity of the data over here is good, then I should be able to just do the inverse Fourier transform on a rectilinear grid using a fast Fourier transform and get the picture. Right? We're not gonna look at the Prince and Links notation right now. We're gonna look at this. So let's look at that inversion. Okay. Here's my function uxy. Right. This is its analytical Fourier transform. Okay. And we're going to, in terms of our experiment, we're going to have, it turns out, samples of this thing once we take the Fourier transform and the projections. So if this is its analytical Fourier transform of my object, then the inverse Fourier transform of this thing gives me the object. Right? So remember, this is the formula for the inverse Fourier transform. There is not a negative here. And we integrate with respect to the spatial frequencies. And x and y are just parameters here for these coordinates. So for every x and y, I do this integration over the whole domain of the Fourier space, and I get a value using the Fourier transform as my kernel here. So we can express this Fourier transform in polar coordinates. So let's just write down the Fourier transform in polar coordinates. Right? It turns out to be this, where we've substituted, variables for kx and ky, right, in terms of theta and k, or this is k in this direction, this is theta. So we've just related kx and ky to theta and big K, and it turns out that this kxx is just xk cos theta, and kyy is just yk sine theta. Okay? However, in going to polar coordinates, and this is the key thing about the whole thing, because of this density issue, the Jacobian of that integral, when you transform into polar coordinates, has a k in it. Right? So the Jacobian is k dk d theta. Right? And you recall when you're doing integration in second year calculus of multivariables, when you go into a different coordinate system, you need to calculate Jacobian if you're going to do an integration. Right? Because the unit of volume geometrically is different as a function of position in space. In Cartesian coordinates, the unit of volume is always just a little box, right? Which is basically dx, dy. When you go into polar coordinates, the unit of volume is a little pie-shaped thing that you have to put in a k here in order to get it right, to get the integral right. This is the essential insight to how we're going to change our back projection algorithm to make it work, right? It's the fact that there's this k weighting here, right? And so basically, because instead of 0 to 2 pi, we're going to do this 0 to pi and put an absolute value of k. Why can we do that? I don't know.
Because it's symmetric?
I guess it must be symmetric, right? GK must be, this must be symmetric. Yeah. I'm going to come back to this. I'm going to remember. This is symmetric in K here. Is it?
From the note. From G.
Oh, here, down here. I just have to read my own notes. Okay. GL theta pi. Oh, okay, yeah. Of course, yeah. So it's actually not symmetric. It's like g of minus L theta is just G L theta plus pi, right? So when we go right around, we've just made L negative L when we're 180 degrees. And so this 2 pi, you can just go 0 to pi and take the absolute value. Okay, great. Thank you for reading down the slide for me. Okay, so we now have this. We've got our object. This is our goal, right? We want a really good estimate of this. We have these, right? Because we measured them. We measured the GL theta and we took the Fourier transform, so we have these guys, right? Or samples of these guys. So we can take the Fourier transform of that thing, but remember we have to put this K in there. So if we go back to our back projection example, so here's mu xy. This is our target. We want to image it. This is what we've measured. This is the Fourier transform, the inverse Fourier transform to get there. This we can move to like couple it as a integral over k here. So we're just going to do the integral over k first, this thing here. And that's going to give us a function of L where what we have to do now is integrate over theta, right? So this thing here, right, is this function g star L theta. And it's basically, we can look at this and just come down here and write it out, where we have absolute value of k, gk theta, e to the, this looks like an inverse Fourier transform, right? So what theorem are we going to use here, right? We know that if I take the Fourier transform of the product of two things, it's the convolution in the spatial domain, right? So my product is absolute value k times gk, right? So when I look at what the Fourier transform is there, it's the continuous Fourier transform of this guy, which is GL theta, our original projection function, convolved with the inverse Fourier transform of this thing, which is just absolute value of k. What's the absolute value of k look like? This function, right? It's pretty simple. It just starts at 0 and goes up linearly, like y equals x, right? From the origin, right? So it's just it's called a ramp, this thing. So it's the inverse Fourier transform of a ramp, right? And this tells us what we have to do in order to get mu xy. We don't back project the GL thetas. We back project this G star L theta. And G star L theta is GL theta convolved with this function, which is the inverse Fourier transform of a ramp. Right? And so we need to modify these guys before we back project them. And the way we do that is we convolve them with the inverse Fourier transform of a ramp and then back project them. And that actually will give you the exact image. If everything's noise free and you have enough samples, you'll get mu xy exactly when you do this. And this is called convolution back projection because of this convolution. This is called a ramp filter because it is basically a ramp function in Fourier space, right? And so because it's applied in Fourier space, it's thought of as a filter. And this is a big insight and a big deal because it gives you the correct image as opposed to that blurry one that we got. So this is what the ramp filter looks like in Fourier space, right? So if these are our data, right, actually what we need to do before Fourier transform is multiply them by this function that essentially scales them as a function of distance from the origin. Okay? And you can see that there's a lot, it's sort of proportional to the density of points that we've sampled as we move out. We need to scale or weight the values out here because we have a lower density of those values out here. So filtered back projection or convolution back projection works like the following. If we have a projection, right, we can take its Fourier transform, right, and so that gives us some function like this. We multiply it by the ramp. We take the inverse Fourier transform of that thing, which is the filtered projection, and we back project those. This, I guess I can't remember their full name, but it's been shortened to Romlock because they were the first guys to produce pictures with this algorithm where you multiply by this ramp filter before doing the back projection. And so it's either called a ramp filter or a Romlock filter. And it's kind of a strange thing, right, in that it goes up linearly with spatial frequency, right? But obviously it has to stop somewhere, right? Our data basically stops somewhere, and so it just goes right down to 0 at the highest spatial frequency, and then it's 0 out here. That causes problems, as you might imagine, having a filter that looks like this. It's a very unusual looking filter, right? So normally what do filters look like when in audio and things like that? Most of the time filters are low pass kind of filters, and they have high intensity at low frequencies, and then they roll off nicely at the higher frequencies. Oftentimes they roll off so smoothly that they're infinitely differentiable, and they, have zero slope when they hit 0, etc. like that. This one is anything but that. This filter has 0 at the origin, right? And right before it's going to shut off, it's at its peak and just goes down here. And this is like infinitely non-differentiable. Right? I mean, it's got a big point there. However, analytically, this is the process by which you can recover the actual values of mu x, y. And so we're kind of stuck with it. So the other way of doing it, if you're computing this and doing this in your lab or your machine that you've designed to sell to customers, is you take your projection, right, GL theta here, and you convolve it with the inverse Fourier transform of that ramp function. Right? So we do this convolution, which is equivalent to that on the last slide, equivalent to multiplying in the Fourier domain and taking the inverse Fourier transform. We're going to stay in the spatial domain, and we're just going to convolve with the Fourier transform of the ramp function. All right, this is the convolution theorem in action. So we'll convolve with this thing, and now I have a convolved projection, and I back project those. Right, so everything's done in the spatial domain. I never took a Fourier transform here. I just did a convolution. So what does it look like? This.
Excuse me, could you
Yeah, sure.
say that again?
Yeah.
So in this case,
Yeah.
you took this. The first one is like the capital G L theta, and then the other one is the small.
Okay. Yeah, I should relabel these better. This is little GL theta.
Okay.
Here, right? We take its Fourier transform and we get capital GK theta here.
Okay.
Okay, I'll relabel these. That's a very good point. And then we multiply capital GK theta by the ramp function, absolute K, right? We take the inverse Fourier transform.
Wait, and that thing is the G star.
Yes. Well, this is. The G star is after we do
After
this.
the inverse.
Yeah.
No,
it is not.
Like
It is not.
Yeah.
Yeah. So G star is, let's go back and look analytically. So G star is G convolved with the inverse Fourier transform of a ramp.
Which means that if you go back to that slide,
This guy,
second figure is
Yeah,
right?
G star is going to occur over here in the next slide.
Right, but then the bottom left is small G L theta, or is it capital?
This one?
Yeah.
yeah, this is basically when I take a Fourier transform of this, it's capital G K theta. Okay, so that's our estimate of the Fourier of using the projection slice theorem. It's a sample through the Fourier
Right.
space.
Yeah, I remember that.
Okay, so that's this guy. You multiply it by the ramp
And then take the inverse.
and take the inverse Fourier transform, right? And then we back project those guys.
And instead of the next slide.
This slide, this thing is little g L theta. You convolve it with this, you get g star, right, L theta, and back project those, and you get the same result.
But that is still the f inverse of the ramp function, the second.
This guy
Yeah.
is the inverse Fourier transform of the ramp function.
Okay.
Okay, so this is in the spatial domain. So what I'll do is I'll put better notation on these slides and put them back up on the thing. Yeah, that's a good observation. Okay, so now this is GL theta, right? And it turns out that this projection, can anyone guess what this is a projection of? It's like a circle, a disk, right? And notice the projection of a circle is not a semicircle. That's why. So this is the projection of, say, a disk. When you do the convolution with the inverse Fourier transform of the ramp function, when we do that convolution, this turns into this. This is G star L theta, right? Do these look anything like each other? Not at all, right? So we were back projecting these guys, and then we should have been back projecting these guys to actually get the correct result, right? And that it makes sense because say my object is a disk, right? And I back project all of these. These are all going to look the same if the disk is in the middle. And I back project all of them. Will that disk have a uniform signal across its face? It will not, right? It'll have a peak in the middle and it'll roll off as we go to the edges of the disk, right? So it's already, that's incorrect, right? When I take the convolution of this with the inverse Fourier transform of the ramp, I get this function. And now, this is the edge of the disk, and that's the face of the disk. So when I'm back projecting these things, I get an actual disk, right? The other interesting thing is we have these very steep negative side lobes here, right? And so what these do, in effect, is all that signal that gets projected out into space, this just subtracts that off as we move around. And so it compensates for that stuff that got projected out. That's sort of a heuristic way of thinking about it. So now, recall this is GL theta, right? For that pattern of circles of different diameters that we had in the book. And that's what GL theta looks like. I convolve that with inverse Fourier transform of a ramp. This is the function, just a sample of that function that we get. There's negative values, positive values. It's basically has a zero background, right? So it's almost like a derivative of this function. And back project these guys, and now out here, that truly is zero. That's a good thing, right? So I'm back projecting zeros. And, these things have different positive and negative amplitudes depending on the results. And so here's 40 out of 240, 80, 120 out of 240, we get this. And then finally, we wind up with this function here. Okay. What we're going to look at is this is the ramp function, and this is its Fourier transform. If you use this function just on its own, it turns out that a lot of artifacts and high frequency noise pops up in your pictures because you're really multiplying the high frequency information with a huge amplification, and you're sort of tamping down all of the low frequency stuff. So over the years, people have developed different versions of this, right, to try and smooth out, the issues of getting these really sharp transitions in Fourier space. And here's one. It's a cosine filter that ramps so that at least its derivative is 0 before the transition. This is a Shep-Logan, which is probably a couple of derivatives are 0 as it comes here. And then this one where we actually, instead of having a peak up here, we ramp the whole darn thing down to 0 before reaching our maximum frequency. And so these are the convolution kernels that result from these different filters. And they're often used. Like for standard CT, you'll use a smoothing convolution as opposed to the ramp filter, which often is called bone reconstruction because it preserves the edges of bone. And so here's the image with the ramp filter. Here's the image with, this Hamming filter, and it smooths it out, and it also smooths out some of these edge artifact issues. Okay, so we're going to stop there, and I'll see you next Monday. Okay.